Hey everyone, thanks for joining me again. In this video, we're going to look at a textbook problem from probability theory called the birthday problem. And if you've taken a formal course in probability before, you've likely seen this. In fact, I'm sure you have. But even if you haven't taken a formal course before, you should have a decent background in probability because this video will be hard to follow along with if you don't. We'll be using some formulas that may not be it may not be too easy to understand where they came from if this is your first time seeing them. Alright, so first let's consider a case where you have two people in a room and you want to ask different questions, like for example, how likely is it that they'll both have the same birthday? Of course, you wouldn't think that the probability would be too high. You would think it'd be very small. All right, but before we can calculate the probability, we have to know the size of the sample space. How many different combinations of birthdays can there be for the two people? If you think of just two coins rather than two people, each coin can only take on two values, right? Either heads or tails. So if you have an experiment where you flip both coins, you only have four possible combinations. You could have tails tails, heads heads, heads tails, or tails heads. Right? But with the two people, and we're talking about birthdays, and we're not considering leap year here, of course, each person can take on 365, one of 365 possible values, right? So if you think of the person as a variable, then all 365 values are possible. So the total number of combinations of birthdays here between the two people would be 365 squared. And if you have three people, it would be 365 cubed. And in general, it's 365 to the kth power, where k is the number of people in the room, or the number of people you're asking. So again, the question is, what is the probability that at least two people in a room share a birthday? Of course, if there are only two people, we expect that probability to be very small. But if there are 366 people, then we know that there's a 100% chance we'll find we'll find two people with matching birthdays. Right? So we're looking really at the range of people in a room between, say, 2 and 365. So the naive definition of probability tells us that the probability of a specific outcome is just given by the number of ways to have a specific outcome divided by the total number of possible outcomes. The total number of possible outcomes being your sample space. And counting the number of ways to have a specific outcome can be very hard, if the problem is fairly complex. You have, say, two people, each person can take on 365 different values. Of course, nobody actually has 365 different birthdays, but before we ask them what their birthday is, we don't know, so it can be any one of those values. So counting the number of ways to assign birthdays to k people such that there is a match is pretty hard. And it's a lot easier to count the number of ways to assign birthdays to k people such that there isn't a match. Right? So if you think about having a set of cards numbered 1 to 365, so that you have 365 different cards, and you have a number of people in the room, and you ask them each to draw a card and not replace it in the deck, then no two people can have the same card. Of course, that means if that number on the card corresponds to a birthday, no two people can have the same birthday. All right, so that's kind of what we're looking at here. And we calculate that just using this formula here. And like I said, if you've dealt with probability before, you've seen this in, say, poker hand probability examples. So we know that assigning birthdays to an increasing number of people, k getting larger and larger such that it goes from, say, 300 to 320 to 330 to 350 to 360 to 365, we know that the probability is getting closer and closer to 1 if we do that. And then if we have more people than there are possible birthdays, meaning k larger than 366, or equal to k equal or larger to 366, then the probability of finding a match is 1. So we're concerned with a range of people between 2 and 365, including 365. All right, so as k gets larger, the probability goes to 1. And as k gets smaller, as k goes towards 2, the probability goes to 0. So to find a value in that range, what we can do is we can take the total probability as k gets larger and larger, meaning over time you'll get to a probability of 1, and then subtracting the probability of not having a match, which we can easily get, again, from this formula here. All right, so we use this formula to get the probability of having at least one matching pair of birthdays. So a question that is often asked in the birthday problem is, how many people would you need in that room to have a probability of a match that meets or exceeds 0.5 or 50%? Right, so we can just set the probability equal to 0.5 and then solve for k. Now you might think just off the top of your head, well, if you've got 365 possible birthdays, maybe just cut that number in half and you'll have maybe 180 something people in the room necessary to have a 50% probability of a match. But actually you'll find out the result is much different, and for most people it's counterintuitive. Alright, so to look at things, I'm going to open up a Jupyter notebook here, and we're going to do this in Python. We're going to kind of experimentally verify some results. Now if you solve this equation here, the number you're going to get, and I'll reveal that to you in a little bit, but if you want to go ahead and solve it now and find out for yourself, go ahead. I just don't want to spoil the surprise. But once you do that, you're going to get a number, and we're going to verify that using Python. So I'm going to open up a Jupyter notebook here. Okay, and I'll just rename this quickly. B-Day problem. Alright, so, and let me go ahead and just label things here, so if you look at the notebook later, we'll be able to follow along with the code and what we were thinking. Alright, so what we'll need to do is import, first of all, the random module. And that we'll be able to use that to simulate asking random people, their birthdays. And we'll need to find a way we'll need a sort of like dictionary of months and days so that we can easily get a random birthday. We can calculate a random birthday. So what we can do is we can create a dictionary object. We'll call it months and days. All right, and then for the keys, we'll assign the months, and we'll just use 3 letters for each. Makes it easier. And then we'll also, for the values, have to give it a total number of days in the month. All right, so for January you have 31 days. For February you have, and we're not counting leap years, so we'll say 28 days. March, 31 days. April, 30 days. May, 31 days. June, 30 days. July, 31 days. Remember, July and August have the same number of days. Both have 31 days. All right. Okay, what do we do wrong here? All right, hopefully that's good. All right, no errors that time. So now what we need now is a function to get a random birthday. All right, so let's label, or at least explain what we're going to do here. So we need a function, and this function gets a random birthday. All right, so we'll define that function. We'll call it random bday. All right, so first we want to get a random month. All right, so we can define a variable, and we'll call it random month. And we'll use the choice function in the random module. So we use random.choice. And then what we need to do is we need to grab a value, an element from a list of elements. So we'll take all of the keys in our months, days object above, or dictionary above, and then just get the a random month from that list. So we'll turn it into a list. All right, we'll also need a random day, so we'll use the same logic or the same thought process. Sorry, we're not going to use random choice because we know for each month how many days there are in the month, so and each day is represented as an integer, so we can just use randint. Alright, so some random integer between 1 and the total number of days in the months, which comes from our object above. And we need to input the random month so we know that we're actually getting the correct number of days. And then we can just return that birthday as a tuple. Right, no errors there. Now we need a function that will give us a list of random birthdays. All right, using the random birthday function. Right, this random birthday just generates one random birthday, so we'll need a function that generates an entire list. And so this won't be a large function. We'll just call it list of bdays. And it takes in a value, and that value is the number of people, right? What we were calling k earlier. And it returns a list of random birthdays. So we can just use a list comprehension here. Alright, so now if we have a list of random birthdays, we need to check if there's a pair, right? So we'll go through the list and then we'll try to find a pair. Right, so this will probably be our most involved function, although it's still not that difficult. So we'll call our function check for match. Right, and it just takes in as a parameter the birthday list that we create. And that'll be fed in at a later point. Alright, so first we'll create a variable called match. It's a Boolean variable. We'll set it to false. And then what I want to do is I want to check to see whether or not I have a matching birthday in a list. So what I'll do is I'll take my birthday list and I'll go through it one element at a time, and then I'll look at all of the elements after that one. So for example, if I'm checking the ith element, then I want to look at all elements in the substring I plus 1. And well, the substring that starts with the value I plus 1, I want to check all those elements, the rest of the elements in the string, and find if I have a matching birthday or not. Right, so you have to use a double for loop. So I'll say for I in range length, and that'll be the birthday list. Right, but remember, we're checking the ith value against the I plus 1 value, or the I plus whatever. Ith and I plus 1. I can't really come up with a way to say that. But basically, we're checking the value at I against the value at I plus 1, and we're looking for a match. So when we're looping over just the i's, we'll have to subtract 1 because we don't want to go out of the we don't want our index to be out of range. And then now we'll have to loop over that substring that starts from I plus 1. Alright, so we're going to compare the element at I against the element at I plus 1. So remember, we're comparing tuples here. Alright, so the first element in the tuple from the element in the birthday list at I to the first element in the tuple in the element at the birthday list at I plus 1. That sounds pretty convoluted. Sometimes it's best just to read the code and not try to explain it too much. All right, so this is our condition, right? We're going to check for a match here. So if you look up here, our birthdays are tuples, right? With months and days. So first we're comparing the months in the ith element to the element at I plus 1. So we're comparing the months. That's what these zeros are. Right, the first value in the tuple. And then we're comparing the day, right, which would be the second value in the tuple. And this is in the ith element. And then this is in the element at I plus 1. So these are the days. So ones are the days and zeros are the months. All right, and if there is a match, we just set match equal to true. And that's it. Of course, we want to break. We don't want to find all the matches. We just want to know if there's at least one, so we can just break out of the loop. All right, no errors there. All right, so now what we'll want to do is we'll want to take a certain number of people and we'll want to we're going to have a bunch of different trials, right? So for example, if we have 10 people, we'll create a list of 10 random birthdays and then we'll look for a match, and then we'll do that again, right? We'll create another list of 10 random birthdays and check for a match, right? And then if we do this, say 100 times or 300 times, we'll get a pretty good idea of how many matches we could expect to see on average for a group of, say, 10 people or 20 people. And so we'll have two variables, right? It'll be the number of people and the number of trials that we're going to run. So this function gets a number of matches for a specific number of people in n trials. So I'll call this function number of matches, or num matches. Right, it takes in those two variables, right, which would be num people and number of trials. It's probably not good practice to use the function name as a variable name as well, but I'm just going to do it anyway. All right, so what we need to do is, remember here, what we're doing is we're going to create a list of birthdays, and then we're going to run through that list and then find out if we have a match, right? And if we have a match, we're going to get a value of true, right? And then what we would want to do is find out how many different true values we would get, in a certain number of trials. So we could first throw in a list of birthdays with a specific number of people and check for a match, right? That'll be just one thing. So this is going to end up being a list comprehension, but basically you'll have the function check for match with a list of birthdays. All right, so we're feeding in the list of birthdays function to our check for match function. Right, and the list of birthdays takes in number of people. All right, but we want to do this not just one time, we want to do it a bunch of times, right, for n trials. Okay, so that's just going to give us a list, right? That list isn't going to tell us anything about a probability. What we're going to do is we're going to count the number of matches, and then divide that by the total number of trials, and that will give us it'll give us a probability, right, of finding. It'll give us a number that represents or approximates the probability of finding a match given a certain number of people. So what we can do is use the sum function here. So this is just calculating a mean. And so we'll have to divide that sum by the total number of trials. All right, we don't have an error there. Okay, good. So, excuse me, rather than just calculate a bunch of numbers, we could look at things graphically to make things easier. So we'll go ahead and use matplotlib. Let's label first. All right, so first import matplotlib. All right, and we'll look at, let's say, just first 10 people. And how many trials should we do first? Let's do 100 trials. All right, so we'll need an input array for our chart. It's capital X. All right, so we'll generate 10 values there. How are we going to chart our probabilities? Well, I guess we can just grab values of X from our X list and then calculate the number of matches using that. All right, so each value on our X list would just be a certain number of people. All right, so that means that this K value up here isn't really representing the number of people, so I think I probably could have a better variable here. Let's just call this P. And let's set that equal to 100 as well. All right, so I'll generate a list of values for Y called match probability. And then we'll just call the function number of matches, which does most of the, or that's calls all the other functions we'll need. Alright, so basically what we're doing is we're using a list comprehension to generate a list, and for each iteration, right, we're calling the function number of matches, we're feeding in a number of people, which will be X from here, right? So we're increasing the number of people from 0 to 100. Yeah, I'm just going to call this K. It gets confusing because the values of K are actually represented by X here, but we'll go ahead and just keep that. And that should give us a graph. Let's go ahead and label it. Alright, let's run it and see what happens. Alright, so that's not good. Okay, list of birthdays is not defined. I saw that earlier. Oh, I see. I was calling it list of birthdays, the function. So where did I put that? List birthdays was a variable, so list of birthdays was the function. And so we've got nothing here. So what are we doing wrong? So, alright, it looks like we're not returning anything here, which is not going to help us, so we should return num matches. And run that cell, and run this. Alright, good. So we're seeing a graph. It's not a nice looking one. But maybe things will smooth out if we increase the number of trials. So we can increase it to 1,000. And then when I run this, it'll probably take a while, so I'll pause the video. Alright, so our graph is a little bit smoother here. And just to make it as smooth as possible, let's increase the number of trials to 10,000, and then I'll go ahead and pause it again, so when the video comes back on, the graph will already be there. Okay, so the curve is much smoother now, and it makes it easier to read. Right, so before the question we asked was, what was the probability, or sorry, how many people would we need in the room to achieve a probability of at least 50%? So one thing we could do to make things easier is to just go ahead and make a flat line at, probability equals 50%. So we can just define a variable and just call it 50%. And then say, let the value be constant. And so that'll be a second line. And then we'll want to plot that as well. I'll go ahead and run that, and again it's going to take a while, so I'll go ahead and pause the video. So we've got our horizontal line here at the value probability equals 0.5. And we can see that the number of people that you would need to have a probability of around 0.5 of having a match, it's just over 20, right? And in fact, if you solve that equation that we had earlier, right? Let me just bring that up. And if you solve this equation here, that would in fact give you a value of k equals 23. All right, so that matches up quite well with our experimental results here. Right, and we can see that for increasingly larger numbers of people, you get to a probability, you approach a probability of 1. Right, and if we set k equal to 366, then this line would just go completely flat or horizontal. And in fact, we get to a pretty high probability of having a match before we even get to 100, right? So somewhere between 60 and 80, we're almost there. So that result is probably counterintuitive, and I think that's one of the most interesting things about studying probability theory is that you often find out that results are much different than you'd expected, and that's what makes it an exciting field of study. So anyway, I hope this illuminated the birthday problem for you a little bit, and gave you a chance to see how you could easily experimentally verify theory from probability, and that's what we're going to be doing in upcoming videos as well. All right, so thanks as always for joining me, and I will see you next time. Cheers.